Hello, everyone. We're at a big transition in terms of material today from conventional symmetric cryptography to what's called public key or asymmetric cryptography. It's something that people for a long time thought was impossible, and it was eventually realized through the use of mathematical techniques from number theory. It's a quite concrete subject. We are used to numbers. We've studied them from elementary school onwards. So I hope it's relatively accessible and fun. But we'll discover new things about them. For example, we'll play with the numbers 1 through 10, the fingers on our hands, but we'll see properties of them that you won't have seen in school. The computational word here refers to the fact that we're going to be interested not just in the mathematics, but in algorithms to do things on numbers as needed for encryption. While the content of the chapter is largely about understanding the basics of number theory and its algorithms, let's start with some motivation to see where we're going. This is the problem which motivated the introduction of these tools. And it's pretty basic. It's called secret key exchange. We've seen that if Alice and Bob have a shared key, they can use that to encrypt information they send each other, authenticate it, and so forth using symmetric cryptography. But how would they arrive at such a shared key? So what if we pose the problem of Alice and Bob wanting to communicate over a public channel in such a way that at the end of the communication, they would be in possession of a shared key, but it would be secret in the sense that an adversary who was witness to their entire communication did not actually have that key. The protocol would specify steps for the parties. For example, Alice may pick some quantity little x, perhaps at random from some set, maybe in terms of that define some other quantity big X, and then transmit that to Bob. Bob would likewise make some random choice little y, maybe compute some big Y based on it, and transmit the latter over to Alice. The protocol now is supposed to give us functions, public ones, f sub a and f sub b. Alice applies this function to this, which we view as her secret, and what she received from Bob. And Bob likewise applies his function to his secret and what he received from Alice, and each of those outputs a key. The properties we want are that Alice and Bob end up with the same key. Well, that's not hard by itself. What makes it much more interesting is an adversary who sees and witnesses everything sent on the channel, which is big X and big Y, doesn't know what this key is. Now, we can try to solve this problem, and for a long time, people did try and were very interested in doing that because that would give them a way to leverage symmetric cryptography. You could try to use block ciphers, encryption, and everything we know. And to cut a long story short, you're probably not going to succeed with those techniques. While symmetric cryptography has existed now for thousands of years in some form, starting from substitution ciphers, nobody in that time discovered any way to securely implement this kind of secret key exchange to the point where people thought it was impossible. But in the late 70s, Diffie and Hellman found a solution, and that was the birth of what we now call public key or asymmetric cryptography. And their breakthrough was done using number theory. This is a pointer to a YouTube video, which is kind of a fun layman's way of explaining the protocol. But what I'll do instead is I will try to show it to you. And I think what's quite interesting about it is that even knowing next to nothing about number theory, we can get a fairly good idea of how that protocol actually works. And a lot of the rest of this chapter will be spent filling in what we see here. So in this protocol, we assume certain things are public and known, One of them is a large prime number. Now, when we normally think of numbers, you may think large means something like, 1,000 or something like that. But this is, from that perspective, unimaginably large. It's a number whose bit length is in the many hundreds to thousands, or if you like, hundreds of digits big. Another number that's public is something denoted G and called a generator mod P. At some point, we'll know what that means. For now, imagine that G is simply the number 2. This set is all the numbers between 0 and 1 less than P minus 1. And here's the protocol. What Alice does is pick a random point from this set, call it little x, and then she raises G to that power. So we know what this means. You just multiply this G, which is for us 2, by itself x times. X is an integer. That makes sense. But she's not interested in the integer end product. She wants to take the result modulo the prime number P here, and that's called big X. That's shunted over to Bob, and Bob does likewise. He also picks his own little y secret and then raises G to that power, takes the result mod P, and sends the corresponding big Y over to Alice. And now comes the number theory magic. Let's look at this quantity. This is our public G raised to the power the product of the secrets of Alice and Bob. There are two ways to write this. Clearly, it's the same as if I'd written first taken G to the X and then raised it to the Y, or first taken G to the Y and raised the result to the X. While they are mathematically the same, algorithmically, they're quite interestingly different. Because looked at this way, it's what Alice sent to Bob raised to Bob's secret value, and thus it's something Bob can compute by himself. And that's what he does here, and call the result K sub B. When looked at this way, it's something Alice can compute, because it's what Bob sent her, G to the Y, raised to the power the secret that she knows. And so we can write it like this and compute it like this. And we will set this to the shared key. Now, what about the adversary? The adversary's job is to take the big X and big Y, which are respectively G to the little x mod P and G to the Y mod P, and try from them to figure out what this is, modulo P. And our sense, or the sense of a lot of experts and one that has developed over time, is that adversaries will have a hard time doing this as long as the P and the G are properly chosen. Of course, we'll have to justify that claim a little bit as we go on. And so there it is. This is the magic of Diffie-Hellman key exchange. It's one of the gems of cryptography. It's one of, if you remember a few things from the class to take away with you, this might be one of the more interesting things to remember. Now that we've seen the idea, though, suppose we want to implement it or understand it a little better. We see that there's a lot of questions we could ask ourselves. For example, where do we get these humongous primes? They're hundreds of digits long, and it's not obvious how to get a prime number of that size. We said it needs to be large, but why and how large? We said G was a generator modulo P. What does that mean? What are the properties of a generator and why are they relevant? Once we know that, how do we find one? I said 2 would be one. That's sometimes true, sometimes not. We gave Alice and Bob instructions, raise G to the power X mod P. Well, if you want to implement this on your computer, you need a good, fast algorithm to do that. It's actually not obvious how that arrives. How are we going to do this computation? And finally, of course, the security element, which is why would it be the case that what we think of the adversary as wanting to do is really something it should find hard. So to answer all of this, we're going to, for a little bit of time, forget about Diffie-Hellman secret exchange and just take a trip into computational number theory. And we'll begin very slow with some notation and slowly start building it up. One of the sort of deceptive things about number theory is that any little piece of it is actually quite simple, but yet when you put it all together, it's quite powerful. And so we have to kind of keep track of everything as it comes along. So by z, we'll denote the set of all integers, negative, positive, and 0. The natural numbers n is the non-negative integers, and z plus is the positive ones, 1, 2, 3 onwards. When we have two integers, positive or negative, we can ask what is their greatest common divisor. That's defined to be the largest integer that divides both of them, and that itself needs to be a positive number. For example, if you're asked what's the greatest common divisor of 30 and 70, you notice that 10 divides them both, and nothing larger than 10 does. So that's the answer. Now, mathematicians work with infinite sets quite a bit, but when we're doing encryption, we need finite sets or domains from which to draw things. So we tend to restrict things a little, and this is how we do it. Let's fix a number n, which is a positive integer and is a public parameter. Now I can define the set z sub n to be all numbers between 0 and 1 less than n. The intuition is that these are all possible remainders you can get if you start dividing numbers by n. There's a subset of that which is of interest. In the space of n numbers, let us say that I select and I'm only interested in those whose greatest common divisor with this n is 1. That subset is called Zn with a star. Now, if I ask you what is the size of the set Zn, it's quite obvious. From 0 to n minus 1, there are n things. But what is the size of this set? It's somewhat less obvious. Mathematicians study that and give it a name. It's called phi of n, the Euler phi or totient function. Remember, bars around a set returns its size, so it's the number of points in that set. For example, if n is 12, z12 is the numbers 0 through 11. How do we get z star 12? We look at everything here, and we throw away everything that has a common divisor with 12. Notice we need to throw away 0 because 12 divides 0. 1 is fine. We throw away 2 because 2 divides 12. And also 3 and 4 because they're divisors of 12. And so in the end, what we're left with is these four things. What then is phi of 12 is the size of this set, and that's 4. Now we move into operations. One of those is integer division. Normal division we might envisage as returning fractions. Integer division takes two numbers and returns the quotient and remainder of dividing the first by the second. So a is an integer, so is n. And what it means to divide a by n and get quotient and remainder is to write a as the quotient times n plus remainder, where the definition of the remainder is it has to be non-negative, but strictly less than the number by which you're dividing. And once you have a remainder, you might notice that that's just a mod n. That's the definition of a mod n. So in particular, this enables us to compute mods. If I ask you to run integer division on 17 and 3, you would divide 17 by 3 and notice that 5 times 3 is 15 plus 2 is 17. So the quotient is 5 and the remainder is 2. Sometimes we're not so much interested in the magnitude of a number itself as to whether two numbers have the same remainder when divided by some third number. If a and b are numbers, I'll write a is congruent to b mod n if when you divide a by n and divide b by n, you get the same remainder. For example, 17 and 14 are congruent modulo 3. Why? 17 mod 3 we just saw is 2, but 14 mod 3 is also 2. There's a abstract mathematical object or construct called a group, which is explored in an algebra class in number theory. and has lots of wonderful properties. It turns out that knowing about that and exploiting those properties is quite useful for cryptography. So I'm going to tell you what these groups are. Some of you will have seen these before from your math classes. Maybe for others it's less familiar. When we want a group, the first part is a non-empty set. In our case, often finite, but not necessarily. The second element is what's called a binary operation on the set. That's just a way of saying that if I give you 2 points in the set, you can compute a value based on them through this binary operation. Now, one of the intuitive elements of groups is that they are, in some sense, very familiar. We've seen a lot of them starting again very early in school, but not under this abstraction. So once you start seeing examples, they will be a lot more familiar. Now, the set G is a group under this operation if it has a set of 4 properties called closure, associativity, identity, and inverse. And we'll present those in a bit. But first, we may as well look at some examples to make this concrete. In this case, I fix a number n, which is positive, and I will define a group which depends on this n. I first need an operation, and I'll pick a simple one. Given 2 numbers, I will add them and return the result modulo n. And I think of the space of numbers I'm interested in as being Zn. So for example, suppose n was 6. Then the numbers of interest are 0 through 5. And this table shows the result of adding the row and the column elements and taking the result modulo 6. For example, 2 plus 3 is 5 mod 6. 3 plus 4 is 7, and 7 mod 6 is 1, and so forth. You might notice a bunch of nice properties of this table. For example, it's symmetric. What that means is that this first row and this first column are the same, and so forth. Our claim or a fact is that this set with this operation is actually a group. It will have all the properties we need. A more interesting example for cryptography is what's called the multiplicative group modulo n. Again, we have some number n to parameterize it, but our operation has changed. It's not addition, it's integer multiplication, except we return the result mod n. So, for example, if we set n to 12, then the operation would be multiplication mod 12. The second change is that we change the set. It's no longer Zn, but Zn star. And remember, that means everything from 0 through n minus 1 that has no common divisor with n. When n was 12, we worked this out by checking one by one all the points in Zn to see that Zn star looked like these 4 points. So let's again create a table showing the results of the operation. So for every a here and b here, I will write a times b mod 12 here, but I will confine myself to those a's and b's that fall in the set of interest. So for example, 5 times 5 is 25, and 25 mod 12 is 1. 5 times 11 is 55, and 55 mod 12 is 7. Again, the claim will be that this set, Zn star, under multiplication mod n, will meet the axioms of a group we give next. Okay, so then what are these axioms? The first one is called closure, and what it says is that when you have this set G and our binary operation, it tells you that you can take any 2 points and compute a result through that operation. And closure simply asks that that result is itself a member of our starting set G. It's back inside the group. It isn't the case that that's always true. For example, that I suppose I set this set to Z6, and I define the operation to be regular integer addition. Well, then there isn't closure. 4 and 5 are in Z6, but their sum is 9, and 9 is not in Z6. I can fix that by taking not just plain addition, but doing a mod n at the end of it. And since anything mod n is between 0 and n minus 1, it's clear that under this operation, the set Zn is indeed closed. That verifies the first group property closure for our first example, what we call the additive group. Now let's turn to what we call the multiplicative group, which is Zn star with the operation of A times star B being A times B, taken mod n. And we want to claim that again there's closure. It's somewhat interesting that this claim is non-trivial. In a math class, you would spend a little time and actually prove it. Why non-trivial? Because what it's saying is that if A and B are in here, meaning have a greatest common divisor with n that is 1, then the product mod n is also in here. It's clear that the product mod n is between 0 and n minus 1, but why would it have a GCD of 1 with n? Well, the claim is that it actually does. Now, we can maybe go back and see in our examples how we would verify closure. And it's exhibited here simply by the fact that if you look at the entries in the table, they are all inside this set. No entry in the table is outside this set. And that's all that closure actually means. Next property is called associativity. This is again a property that you've used implicitly many times, likely, but you didn't give it a name because it was kind of obvious. What it says is that if you want to operate on three things like A star, B star, C, then where you put parentheses doesn't matter. I can write it as A star B and get the result and then do a star C, or first operate on B and C, get a result, and then do it with A. The details of the computation may not be the same, but associative says that the end result must be. We can again check this for our two examples. Suppose we pick the additive group, so G is Z mod n. Remember the operation there is an times A star B is A plus B mod n. What does associativity say? It says if I have A, B, and C, and I do A plus B mod n, and then add C and again do mod n, is the same as if I first operated on B and C, meaning added them mod n, got that result, then added in A and took the mod n. It's not hard to check that this is true. And similarly, if we look at the multiplicative group Zn star, where the operation is to take the numbers and multiply mod n, what associativity says is I can first operate on A and B, get their product mod n, and then pull in the C and do the mod n. Or start with the B and C, get that result and pull in A. It's not as trivial as it looks, perhaps, in the sense that when you do the computation, you will see different numbers emerged. For example, suppose n was 12, so we're working in Z star 12, and A, B, C are respectively 5, 7, 11. If I want to multiply 5, 7, and 11 mod 12, if I first do 5 times 7 mod 12, it's 35 mod 12. 35 mod 12 is 11. Now I pull in the 11, multiply by that, I get 121, but 120 is 10 times 12, so the result is 1. If I do it in the other way, I start with 7 and 11 and multiply those mod 12. And now I get 77 over here. 77 mod 12 is 5. Then I pull in this 5, and I get 25 mod 12, which is 1. And what associative is saying is, look, they're the same, but notice that the computation wasn't. Sometimes group properties are easier to understand with non-examples than examples. So we could ask, can you give an example of a group, or not a group, actually a set, and an operation on it where closure is true, but associativity is not true. So the typical things we work with wouldn't do this, but here's one. I will take this time an infinite set, all positive integers, and I define a star b to take a and raise it to the bth power. That, of course, is another integer, so it's an operation that has closure. For example, 2 star 3 is 2 to the power 3, which is 8. How do I show it's not associative? Again, in a little exercise in logic, associative says for all triples A, B, C, you can compute A times B times C with parentheses wherever you want. To show non-associativity, all I need is a counterexample, one triple for which that fails. So the counterexample I'll pick is the numbers 2, 2, 3. Now, let's look at doing the computation so that first I operate here, 2 star 3, and then later with the 2. Okay, 2 star 3 we already said was 8. So now I'm looking at 2 to the power 8, which is this. In the other order, I first operate on these two. 2 star 2 is 2 to the power 2, which is 4. And star 3 means I raise that to the third power, so 4 to the power 3, which is 2 to the power 6. And notice they're not equal. So we did not have associativity. We move to the next property of groups, which is that there should exist something called an identity element. What does that mean? That there is an element of the group which we'll denote as 1 with a G subscript, and operating on that with some other group element leaves your group element unchanged. In other words, A and star with that, or in the other order, it doesn't matter, will just give you back A. That tells us why we denoted it like this. If you think of star as multiplication, then it's playing the role of a 1. Multiply anything by 1, you don't change it. But this is more general. It's saying in our abstract set with its abstract operation, there should be some point that has this property. We can again understand and verify it through our two examples. In the additive group, where G is the set of integers between 0 and n minus 1, or Zn, and the operation is addition mod n, I claim that the identity element is actually 0. 0 is indeed an element of this, and when you operate on A and 0, the operation is now plus. You notice it doesn't change anything. Anything plus 0 is itself, and that doesn't change if you do mods. So we found an identity element. When the other group, multiplicative one, Zn star, and our operation is multiplication mod n, the identity element is now the integer 1. Why? Because for multiplication, it's multiplying by 1 that doesn't change the original number. A times 1, 1 times A are the same, they're A, and mod doesn't change anything. So it was quite easy to find identity elements there. The last property is the one that's the most interesting, and effectively it says that there is a equivalent of what we might think of as 1 over A in a group, something that plays the role of an inverse. But in this case, it's defined abstractly in the group domain. So we have our set and operation on it. And we know that there exists an identity element, which we defined or denoted like this. So inverses says that whenever you give me a point A in the group, I will be able to find some value B also in the same set or group, such that they neutralize each other, in the sense that when I operate on A and B in either order, I get back the group identity element. When this is actually the integer 1, then you can roughly think of B as 1 over A, but you have to be a little careful about using that kind of analogy or idea, because 1 over A isn't necessarily defined in the usual sense that we imagine. But in any case, that intuition leads us to denote B, the inverse of A, with this notation, A inverse. And that, of course, assumes that the group and operation are fixed and understood. So what are these things? Well, again, we check our examples. So if n is some positive integer and g is z mod n, and our operation is addition mod n, then what is the inverse? Well, if I'm asked for the inverse of A, what I want is something which, when added to A, gives me back what? The identity element. But we said that the identity element in this group was a 0. So something which, when added to A, gives me back 0. Well, it's quite simple, right? It's negative A. That's close, but remember it has to be that this inverse is back in the set Zn. So negative A needn't be, it's a negative number, but we can write n minus A, remembering that the n is going to go away because we do mod n's. So why does this work? Because if I add this A and B, I get A plus n minus A, which is n mod n, which is 0. Now we can turn to the multiplicative group. In that case, the claim that it really is a group says that if you hand me any A, and now with the operation being to take the product mod n, it's possible to find a B such that it lies in the same set Zn star, but when I multiply them and mod n, I get back what's the group identity element in this case, which is the integer 1. Now, in this case, I sometimes, for emphasis, write the inverse this way, just to tell you and help appreciate that it does depend on this value here, because that's what defines the group in which you work. All right, so again, given an A, the inverse is some B, and it will be unique, such that when you multiply the mod n, you get 1. And it has to be something that falls back in the same set over here. Unlike in the additive case, it's not entirely obvious how you would get this. So let's try to get some practice by looking at some cases. So here again, we're back to our example where n is 12, and Zn star, which we computed, is these 4 numbers over here. And this table shows us the multiplication or group operation for every group element here and other group element here. The table entry is A star B, or in other words, A times B mod 12, as we saw before. Now we said that every A has an inverse. So in other words, for all of these things, I should be able to find an inverse, which I write as A inverse mod 12. Its definition is the thing which, when multiplied by A, gives me a 1 mod 12. So how would I find that? Well, here is the result of multiplying A equals 1 by everything in the group. So what I'm looking for is, what is the thing that results in a 1 output here? Well, the 1 appears here, so this is the inverse. And that continues. So how do I find the inverse of 5? I scan here to find a 1, and then look what gave rise to it, so 5. And if you keep that up, you see that since the 1s are on the diagonal, the inverses in this case happen to equal the numbers themselves. One of the things to not do is think right as for the inverse, something like 1 over 5. It has to always be a point that's inside this set, hence an integer. Now, one of the kind of fun things to think about number theory, and also great for getting good practice, is to start playing with the numbers and doing computations by hand. And you will soon see that you can do them using tricks for quite large numbers. So let's get some practice by saying I'll pick a slightly larger value of n, like 17, and ask first, what is Zn star, Z17 star? It's all numbers from 1 through 16 that have no common divisor with 17 by definition. But 17 is a prime. So if I look at numbers 1 through 16, none of them have a common divisor with it, with 17. So in fact, it's all numbers 1 through 16. Now let's look at our multiplicative group operation. A star B is the product of A and B mod 17. And I'm not this time going to write down the whole table. I want you to just determine straight away what is the inverse of 2. 2 is in this set. It should have an inverse. How do we approach that? We remember that by definition, the inverse is the value B in this set, such that when you multiply it by 2 and take the result mod 17, you should get back a 1. Well, it's not hard to find this, given that we know that the candidates are only in here. And we can even, use a little ingenuity and see, how can I make sure that 2 times B is 1 mod 17? Well, you could just do trial and error, or you could notice that 18 is 2 times 9, and 18 mod 17 is 1. But either way, the answer is 9. You can check that 9 times 2 is 18, 18 mod 17 is 1. So you might do that by trial and error. But let's try something maybe a tad more interesting, where I ask you in the same group to find the inverse of 4. The approach is again the same. How do I solve the equation 4b mod 17 is 1 for the unknown b? You could again just trundle through everything from 1 through 16 until you find the answer. You're bound to hit it at some point. Is there anything we can do that's a little more clever? So I claim there is. What we can do is notice that if we look at 4 times b as an integer, before we take the mod, in order for that mod to be a 1, that integer must be of the form a multiple of 17 plus 1, because those are the things which, when taken mod 17, give you 1. What multiple of 17? Doesn't matter. Anything would work for this equation. But we can see what they are. The multiples of 17 plus 1 are things like 1 when n is 0, 18 when n is 1, 34 plus 1, 35 when n is 2, and so forth. Why is it helpful to compute these? Because now we can look purely at the integer equation, 4 times b, and it has to equal one of these. Well, whichever one it equals has to be divisible by 4. Otherwise, you can't have 4 times b equal it. And the first one that is the 52. So since 52 is divisible by 4, and we can write it like this, then the answer is the 13, because 4 times b is 52. And as per this mod 17, that's 1. So if you have to compute some inverses, that's an approach you might try. Okay, we're done with defining groups at an abstract level. So let's just remember that we have a bunch of examples, and two very popular ones we'll use, the additive and multiplicative, both parameterized by an integer n. In the first, the operation is addition mod n. In the second, multiplication. In the first, the set is Zn, and in the second, it's Zn star. That's not the only examples of groups. You can get groups, for example, working over strings. G could be the set of binary strings of length n, and define the operation as bitwise XOR, and you can check the group axioms are true. You might note that it's important that it's XOR. If I change the operation to a bitwise AND, you will no longer have a group. Now, again, one of the things that's kind of fun with this domain is getting to play with numbers and have fun with tricks that enable you to do it fast. It gives you familiarity and quick answers. So here's one of those. It's called the just-in-time mod principle. And it considers that you have to add a whole bunch of numbers, mod n. So the naive way of doing that is to just first compute the sum and then do the mod. For example, if I have to do 17, 9, 10, and 16, I add them up. 17 plus 19 is what? 36, plus 10, 46, plus 16, 62. So it was a bit of a pain. Now I have to take this and do a mod with n, and n here I set to 21. So You have to compute that. And you can, and it's 20. Instead, we can appeal to this fact. And what it says is you can do the mods as you go along. So in other words, over here, I first do 17 plus 19, which is 36. Instead of taking the 36 further, I immediately do a mod with 21, and that'll only leave me with 15. Now I take the 15 on and add that to the 10 over here. That gives me 25. And again, I immediately do the mod 21 to get a 4. Take the 4 on, now add that to the 16, and that's 20 mod 21, which is 20. So abstractly like this, concretely like this, and you see it does help to go faster. It's equally true with multiplication. If I want to compute the product of A, B, and C mod n, I can do it by either the slow way, which is I multiply them all first and finally do the mod, or do the mods as I go along. So as an example, if I have to do it for these 4 numbers, mod 21, the slow way would take each of them and multiply. 8 times 5 is 40, times 10 is 400, 400 times 16, that's a bit of work. It turns out to be this. Now I have to do this whole thing mod 21. That looks like calculator work, but if you plug it in, it turns out to be 16. And here I'll do it easily by hand using our just-in-time principle. The way it works is I first do 5 times 8 to get 40. But now instead of going on with 40, I immediately do a mod 21 and I'm left with 19. I only need to take the 19 forward. 19 times 10 is 190. And I can do a mod 21 with that by noting that 189 is 9 times 21. So the remainder is just a 1. Go forward with that and bring in 16. 1 times 16 is 16, and mod 21 is 16. So same answer, somewhat simpler arithmetic. We've looked at some simple operations on numbers, but when we get to cryptography, the most important is raising group elements to powers. So we're going to study that a little. This is the exponentiation operation. We'll define it abstractly. Here I have an abstract group with an abstract operation called star, and I have a group element. I also have an integer, and I want to define what it means to raise a to that power. So I define a to the power 0 to be the group identity element. And if n is a non-negative integer, I define a to the power n in the obvious way. You just operate on a n times where the operation is the group operation. What if n was a negative number? Oh, well, I won't see it quite that way. I'll say I'll have a negative exponent here, a to the power negative n, by definition, is going to be a inverse multiplied by itself n times. Now, one thing that can be a little tricky here is to recognize that these are definitions. In other words, the meaning of a to the n was not known before we wrote down this equation. Here, you would know the meaning of a to the n in some normal domain if a is an integer and so is n. But a isn't always an integer, and the operation may not be the one you think it is. So we have to actually say what we mean by this, and it's done in these ways. But the nice outcome of this is once we have these definitions, all the things we usually expect and like work. For example, if I have to raise a to the power the sum of 2 integers, then it's the same as raising a to the first power and multiplying or operating with a to the power second power. That's not a fact until it's checked, and we can actually prove it based on these formulas. Similarly, if I have to raise a to the power the product of 2 integers i and j, I can do it by first raising a to the I and the result to the j, or the other way around, first raise a to the j and the result to the I. Why are they the same? Because we know that integer multiplication, I times j equals j times I. Similarly, raising a to the negative I, which by definition looks like this, is also the same as having first raised a to the ith power and then taken the inverse. Again, these formulas are a little too simple in the sense that it's deceptive, but they have a lot going on. For example, these negative signs over here, this is something we define through this. Here, we're referring to the group inverse operation as here. But again, the takeaway is once we have these definitions, things work as they should. Now, another thing to remember about exponentiation, as we have talked about early in the class with type checking, is that A is a group element and N is an integer, a normal integer. Sometimes A is also an integer, but that's not how we are seeing it in this context. So you can play with these things. Suppose N was 14 and we look at the multiplicative group Zn star. And we remember the operation is multiplication mod N. If I want to raise 5, which is an element of Zn star, to the power 3 modulo 14, meaning in this group, by definition, I'm multiplying 5 by itself 3 times and taking the result mod 14. And now I have to compute that, and here I can use my tricks. 5 times 5 is 25, so I have 25 times 5 mod 14. I can straight away reduce the 25 mod 14 to 11 and multiply that by 5 to get 55 mod 14, which is 13. What if I have to raise 5 to the power negative 3 mod 14? By definition, I have to take the inverse of 5 and multiply that by itself 3 times, and then take the result mod 14. So we have to go compute the inverse of 5. Well, we practiced how to compute inverses in groups, and the inverse of 5 is 3. You could do that by trial or error or some other way, but once someone tells you, it's easy to check. Why? 5 times 3 is 15, and 15 mod 14 is 1, so this equation is true, and that's the definition of 3 being the inverse of 5. So here we get 3 times 3 times 3 mod 14, and that simplifies to 13. So in summary, 5 cubed is 13, and 5 to the negative 3 is also 13. Now, we will be working largely over finite sets, and so any such set as the group has a size, the number of points in it. That turns out to be rather important in group theory, and so mathematicians like to give it a special name. It's called the order of the group. So we can determine these orders. For example, if you look at the multiplicative group Z star 21, what is its order? Well, it takes a little bit of work. Remember, this is the set of all points between 0 and 20, which have no common divisor with 21. And it takes a little effort to figure out what they are, but we walk through the points one by one and throw away what? Anything that has a common divisor with 21, which means we throw away multiples of 7 and of 3. So the 3 is not here, the 7 is not here, and so forth. And then we count how many things are left. So we get 1, 2, 3, 5, 6, 7, 8, 9, 10, 11, 12. And so the order of Z star is 12. Another way of saying that is that phi of 21 is 12. Why is that? Because phi of n was defined as the size of Zn star. And putting that in yet another way, we've determined that this phi of n is the order of Zn star. So now these two become synonymous. So this gives us two facts in groups. The first is one of the most basic, which you would encounter, say, in the first couple of weeks of a basic algebra class in a math department. What it says is, suppose I have a group G. It has some order, it's a finite group, and I'll denote that order as m, which is an integer. Now remember, we have exponentiation. That means any point A in the group can be raised to any integer power to get back another group element. What if I pick that power to be this order? Why not? It's some integer. The fact says what I get back will always be the group identity element, or if you like, intuitively 1. Not obvious, that needs a proof, but that can be done. There's an extension of that which extends to arbitrary exponents. Again, we have our group. It has this order m, and we have our point in the group. Now I want to raise it to a power that's actually an arbitrary integer. And what the corollary says is that you never really need to consider very large integers because all that matters is the result of that exponent taken modulo the group order. In other words, I want a to the I in the group. Suppose I first take I mod m. Notice this is operations just on integers. I is an integer, m is an integer. I mod m is well defined. And I simply raise a to that power in the group. The claim is that those are the same. It might, in this case, help to actually see why the claim is true, because there's quite a lot of intuition in the proof. So let's look at computing a to some arbitrary power I. But let's use integer division to write I as the group order times a quotient plus a remainder. The integer division function could have been used run on I and m to obtain that quotient and remainder if we wanted to do this algorithmically. But now we can simplify this. We write it, remember, using our exponentiation rules as a to the power m to the power q, and then that times a to the power r. But this, by the first fact, is 1, the identity element, and anything multiplied by the identity element is itself. So we're left with a to the r. And finally, we know that r is exactly I mod m, so we're done. We could play with that a little bit. So remember that we looked at the example of n being 21, and we computed that the order of the group Z star 21 was 12. Another way of saying it is phi of 21 is 12. It wasn't obvious, but we did the work and we got that, so now we'll use it. So suppose I take 5, which is an element in Zn star, and raise it to the 12th power. Since 12 is the order of the group, it's phi of 21, the fact here says you should get back the group identity element. And here I've specialized these facts to the case of the group being Zn star. In that case, that identity element is just the integer 1. And that fact looks like this. It says if n is any integer and m is phi of n, which is the order of Zn star, then raising a to the power m and taking it mod n will give you back 1. Now with a equal 5 and m equal 12, we apply that and it'll tell us we should get back 1. Again, I took the corollary and specialized it to groups Zn star. So what that means is now for some integer n and for m being phi of n, with the group being Zn star, I take a point in it and I want to raise that to an arbitrary power and I want to work modulo n, meaning in Zn star. And it says I can just, in the exponent instead, use I modulo the group order. Notice that there are two mods. This is the mod that does the group operation. This is the mod we've just introduced to simplify exponentiation. If I want to use that and I set a to 8 and raise it to the 14th power, then I is 14. So the way I would compute that is to take 14 modulo the group order, which here is 12. So that's 2, and so I get 8 squared mod 21, which is 64 mod 21, which is 1. So we were able to do a relatively complex looking computation fairly quickly. This is kind of a fun source of games or puzzles. You could challenge a friend to something like this. Suppose I again recall the corollary. So it enables you to raise a to high powers mod n through this formula. And you know that, but not everyone does. And I ask you to compute 5 to the power 74 mod 21. Now, a priori, that looks pretty daunting because the way you would see it is I have to multiply 5 by itself 74 times, which would be a pretty humongous number, and then take the result mod 21, And that means dividing by 21 some huge number, which is not easy. But what if we were more astute and tried to use this? If we did that, what we would see is we could let n in the corollary be the number 21. And now we can see A as being 5, and so we have matched to this. I now would be 74. So if I want to compute A to the I, this says that I need to take the exponent I modulo the group order. So we would now have to know that the group is Zn star and ask what its order is. Luckily, we know we computed its order as 12 in prior slides. So our computation says 5 to the 74 mod 21 means first take in the exponent, take the 74 modulo the group order. 72 is a multiple of 12. So 74 mod 12 is just 2. So I end up with 5 squared mod 21 or 25 mod 21, which is 4. So it's actually quite powerful. Again, if someone didn't know number theory, they might, without a calculator, be quite daunted by a computation like this. But if you know it, you can get it quite fast. Our next step is the consideration of algorithms on numbers, moving away from pure math to computer science. One of the first things we'll have to consider is that when we measure running time as a function of what do we do it, you know from CSE 101 that you always talk of algorithms that are order n or n log n or n squared or something. But what is this n? Well, different problems will have different things. In a graph, maybe number of nodes, and for a string, maybe its length. But the convention we adopt is when we're operating on numbers, this n is the length of the binary encoding of the number. We will be viewing numbers as provided to computer algorithms in binary, and so the length of the binary string is the thing in terms of which we'll measure algorithmic complexity. The reason to do this is numbers in cryptography are much, much bigger than we encounter in algorithms. They look, for example, like this in magnitude, so they're hundreds to thousands of bits long. In algorithms, your numbers may be 32 or 64 bits long. Sometimes we use the notation of bars around a number to denote the length of the binary representation. So for 7, it's 3 because in binary, 7 is 111, and that's 3 bits. So we will need or use a whole set of different algorithms on numbers. And here's a chart of the ones that we will want. So here I've listed different algorithms, and for each I've shown what are the inputs, what is the output, and what's the running time. You can use this chart, or you will use this chart quite a bit. You'll be referring to it, pulling it up, and just invoking these algorithms in your problem solving. So we start out quite easy with like elementary school operations, take two inputs, integers, and just add them. But while we were told in elementary school how to do that, we weren't necessarily told what was its complexity or running time in big O notation in a kind of algorithmic theory sense. But now we're smart enough to figure that out. And we notice that the way we do the addition is going to take time which is linear in the lengths of the binary representations because we do constant number of bit operations per bit in each of the numbers. And so that gets written like this: length of A plus length of B and a big O on it. What about multiply? Well, again, maybe in middle school, we know how to multiply two integers, but we may not have looked to see what is its asymptotic complexity. It turns out it's proportional to the product of the lengths of the binary numbers. That's not hard to see. You can take our usual middle school method of writing down one number and then writing the other, and then for every bit in the second number, you get a bunch of bits corresponding to the ones in the first number, and then you add the whole thing up. And it ends up being quadratic time, the product of the binary lengths of the two numbers. Integer division, a little more tricky. Remember, it returns the quotient and remainder as we define them. It turns out to also be quadratic time, number of bits in A times the number of bits in the number you're dividing by. Mod is just a special case of integer division. It only returns the R value. So computing A mod n is also quadratic time. Our GCD algorithm also turns out to be quadratic. In fact, there's an extension of it called the extended GCD, which is the one we'll more often need, and returns three things. And that algorithm is just as efficient as GCD. Then there's the mod inverse operation. What does this do? Well, remember we said that every A in a group has an inverse. And in particular, if the group is Zn star, then there's a multiplicative inverse, A inverse mod n. And we computed them, but we did it by hand and various tricks. This says there is an algorithm to do it that runs in time quadratic in the binary length of n. You give it any point in Zn star, and it'll trundle along and output the inverse. We also looked at exponentiations on numbers. That means take a number in Zn, take another arbitrary integer, and raise a to the power little n mod big N. It turns out there's an algorithm to do that whose running time is cubic, or in more detail, it's quadratic in the length of the number relative to which you're doing mods and the length of the exponent. You can generalize this operation to be over an arbitrary group, and when you do that, you can count running time in terms of the number of group operations or the number of star operations, and there it turns out to be linear in the length of the exponent. All right, so now the next thing we'll do is look in a little more detail at these numbers. I don't want to look at all of these algorithms in detail. Several of them are quite familiar and not that interesting, but it's worth looking at a few. And the first one there is this extended GCD. So what is that? Remember that the GCD algorithm, which when run on two integers a and n, would return the greatest common divisor, which we see are d. What the extended GCD does is in addition returns two numbers that we call weights. And their property is that the GCD can be written as a linear combination of the original numbers and the weights. In other words, this number a times its weight plus this number n times its weight would give you back the GCD. Why would we want to do that? We'll see that in a bit. But for the moment, let's just see that we understand what it means. If I run this on the numbers 12 and 20, well, first it's saying what is the greatest common divisor of 12 and 20, and that we can easily see is 4, because 4 divides 12, 4 divides 20, and nothing bigger does. But now we can also see what are the weights. For that, I need to ask, what are the numbers here and here such that 12 times this plus 20 times this gives back 4? A little trial and error will show that -3 and 2 works. 12 times -3 is -36, plus 40 is 4. Notice in particular that these weights can be negative. There's a very famous classical algorithm to compute the GCD by Euclid, and it turns out you can compute extended GCD by much the same method. And we'll very quickly look at that since Euclid's algorithm is so basic. The core idea behind it is to reduce the computation of GCD on larger numbers to smaller ones through division. So say I have numbers a and n and I want their GCD, just GCD for now. What I do is I divide a by n to get quotient and remainder. And then the lemma or the fact is that the GCD of a and n is the same as the GCD of the second number and the remainder we got here. And the reason this is progress is that think of A as larger, well, R is smaller than N. And so we've effectively shrunk the size of the numbers. And if we keep repeating this, we'll get down to a case where the GCD is trivial to compute. That idea lends itself naturally to a recursive algorithm. So here I'll write it for extended GCD, takes A and N, and we'll assume they're not both 0, 0, otherwise things are not well defined. We need a base case, and that will be when the number you're dividing by N is 0. In that case, what is the GCD of A and 0? Well, A, because A divides A and A divides 0. And what weights can I use to write A as a linear combination of A and N? Well, A is 1 times A plus 0 times N, for example. So we can easily return what we need when N is 0. Otherwise, we are able to divide. We can't do that if N is 0, but if it isn't, we can divide A by N to get our quotient and remainder. Now I will run a extended GCD recursively as per the lemma on N on the remainder. And it's supposed to give me back not just the GCD, but also corresponding weights. I want to return the correct output for this call, which means the GCD of A and N and corresponding weights. The lemma tells me that the GCD itself is unchanged. I just copy it. But then I need a way to compute the weights. And these formulas, we won't have to go into details, but can be checked, will correctly update the weights here to be the weights for A and N. The runtime analysis is actually non-trivial, but it turns out that when you do it, it's a quadratic time algorithm. What that means is running time is the product of the binary lengths of these two numbers. It's also sometimes useful to know that the sizes of the weights are not too big. In absolute value, this weight will be bounded by N, and the other weight will be bounded by A. Those are facts that we can refer to, but we don't really have to know all the details. And now we come to something we really do need and use a lot. And one of the reasons we studied extended GCD in a little more depth is that we leverage it to get this. So remember again that in the group Z and star of integers modulo n and relatively prime to n, where the operation is multiplication mod n, we know that being a group, it satisfies the inverse property, which means that given any A and Z and star, there's a unique thing called A inverse mod n. And by definition, it's the unique number, again in the same set here, such that when you multiply the two, you get back 1. And the multiplication is mod n. And we saw examples in which we, through various tricks or just exhaustively, computed this A prime for a given A. But we need to do this in cryptographic algorithms and for encryption and other things that run on very, very large numbers. And we can't do those computations by hand or by guesswork. We need an algorithm. And it turns out we can get one through extended GCD. So now if I'm given A and I'm also given N, and I want to compute the GCD, I want to compute the inverse, what I first do is I ask myself, what is the GCD of A and N? That seems in some ways like a silly question because the answer is obviously 1. Why is it 1? That's the defining property of Z and star. It's exactly the set of things which have a GCD of 1 with N. So why would I want to compute the GCD? Well, I don't really, but it's useful to compute the extended GCD because it gives me weights. If I run that on my A and N, I will get back this triple, and I know that the GCD is A times A prime plus N times N prime. And I also know that the GCD is 1. So now I've written 1 as this linear combination. Now take this linear combination and take it modulo n. When you do that, well, the second term is 0 because it's divisible by n. And so modulo n, I'm just saying a times a prime equals 1. And that's exactly the definition of a prime being the inverse of a mod n. And so we have a very simple way to get mod inverses through extended GCD. Given a and n, we define a mod inverse algorithm to run extended GCD on a and n, get the GCD and weights, throw away the GCD, throw away the second weight, and return the first weight for good measure modulo n. So that will be very useful, and it's also useful to know that this runs in quadratic time because that was the running time of extended GCD. Encryption in number theory most often uses the exponentiation operation. So the next thing we're going to be interested in is algorithms to do that. It also arose, if you remember, inside Diffie-Hellman key exchange, where Alice and Bob did exponentiations inside their part of the protocol, and they would need good algorithms to do it. So we want to know how that works. We'll start again at the abstract level, where you have an arbitrary group with an arbitrary binary operation star. And given a point A in the group and an exponent, remember the exponent is not in the group, it's just a normal integer. And I want to raise A to that power, which will result in a group element. Well, we know the definition of raising A to the power n. It says operate on A n times, kind of the obvious thing. If that's the case, staring at that formula, an algorithm seems extremely obvious. I can start by setting a variable to the group identity element, and then n times take my variable and operate with A on it, or multiply by A if you want to think of it that way. And after n iterations, it will look like this. So are we done? Is that a good algorithm? Well, it's good in the sense that it's correct. Certainly it's going to give the right answer, but it's not good for the purposes of cryptography because its running time is way too high. Remember that in cryptography, the numbers are hundreds of digits long, and that means the same is true for this number n. We are raising to humongous powers, powers that themselves may be of this form, 2 to some 512. That means that this algorithm would run for 2 to the 512 steps, which is prohibitively large. So that won't do it all. If that's what Alice and Bob had to do for Diffie-Hellman key exchange, we would not have a practical protocol. Now, from the more theoretical point of view of algorithms theory, this is what's called an exponential time algorithm. Why is that? Because its running time is roughly order n. And you're used to thinking of n as something small, but when here, remember that we measure running time as a function of the binary length of the number. So order n is order 2 to the power the binary length of n approximately. And so the running time as a function of the length of n is actually exponential. So we now ask ourselves, could there be a faster way to do exponentiation? And a little thought says, yeah, there are some tricks. And here's the idea. We notice that if we want to ramp up, we can do that just by squaring. Suppose I have a and I want to get to a squared. Well, that's one operation or one multiplication. But now if I want to get to a to the fourth, I can do that in one step. I just take this and I square it and I get a to the fourth. And I can square this and get a to the eighth. So I can very quickly ramp up that exponent. So getting to a to the 32 takes only 5 steps through repeated squaring. So what that says is if I want to compute a to the power n, I can do that in just I steps where I is the logarithm of the exponent. For example, for 32, I was 5. Okay, that actually works well, but it's not quite general enough. The problem is that it only works when n is a power of 2, so that I is an integer and we can do I steps. If n is not a power of 2, it's not as simple. You might think that's not a small problem. For example, suppose n was somewhere between 16 and 32, like 23 or something. Maybe we could quickly get to a to the 16 and then just slowly, by multiplying by a, get to a to the 23. But in fact, the distance between these two is still exponential and large, so that would still be too slow. So we do need something a little more clever. And that clever method is called square and multiply. And here's what it looks like. So here I'm going to suppose that the number n to which we want to raise a has binary length 5. I don't know at the moment what the number is, but I'm assuming it's 5 bits long. What that means is in binary, I can write it like this, 5 bits, where this is the least significant to most significant. We know how to turn binary into integer. The decimal or the numeric value of n is this formula in terms of the binary expansion, right? Least significant bit times 2 to the 0, next bit times 2 to the 1, etc., etc. Or expanding that out in the case that we know that n is of length 5, it looks like this. How do I compute a to the power n? Well, we do it in steps. We start by setting a variable to the identity element, and our operation is in each step to square what we had before, and then bring in or multiply by a raised to the power the next bit in the binary expansion of the exponent. So the first time I square 1, which gives me back 1, and multiply by a to the b4. Multiplying anything by 1 doesn't change it, so I get a to the b4. Next step, I would square this. That would give me a to the 2b4, and multiply by a to the b3. Since this is multiplication in the exponents, it's an addition, so it would look like that. And now we start slowly getting the idea. Here we're going to slowly see developing the binary representation of the exponent n. The next time I square this, I get a to the 4b4 plus 2b3, and I bring in a to the b2, so that gets added in, and so forth. And in the last step, what I have in the exponent is exactly this, and hence it's n, and so I have a to the n. That can be, without too much difficulty, written in code or pseudocode, and it would look something like this. We do need a little routine to take an integer and return the binary representation, and I'll call that binary of n. By definition, this is how the bits in the binary representation are defined. So as an example, the binary representation of 20 would look like this. At this point, I'm still writing the algorithm abstractly. G is a group and it has some operation star. Now, this algorithm takes a and n and raises a to the power n. And the way it does it, it just does what we said before. First off is a base case. If the exponent is 0, we know by definition that a to the 0 is the identity element, so that's what we return. Otherwise, we expand and get the binary representation of n, the exponent. We initialize our variable to the group identity, and then we do our square and multiply. We start from the most significant bit, so it goes backwards from position k minus 1 down to 0. And at each stage, we take our variable, square it, and multiply by a to the power the current bit in the binary expansion. And the little example we saw earlier says that this will work. But what we've achieved is quite a lot relative to our naive methods. This, in terms of cost, takes a number of group operations, meaning star, which is k, the k steps in the loop, and k is the number of bits in the binary representation of n. So remember that this bars around n is the length of its binary expansion. So this is now a linear time algorithm and quite fast. Now, very often we use this algorithm in the particular group Zn star, and so it's worth specializing to that group and just rewriting what we get in that case. In that case, I'll call the algorithm mod x, and I will explicitly give it this argument n, which is a way of saying in what group you're working, namely Zn star. And it's supposed to compute a to the power n, little n mod big N. How it's done? Well, it's the same as before. It's just that you make these substitutions where the star group operation is replaced by multiplication mod n, and the group identity is just the integer 1. And that's all you need to do. When it comes to running time, remember that the prior algorithm ran in time order length of the exponent group operations. But now I want a complete running time, and I note that each group operation involves a constant number of multiplications mod n, and each of those takes time quadratic in the binary length of n from our little algorithms table. And so this is what we get in the end for the total running time. And notice that that's cubic. And this is a fundamental fact in computational number theory and encryption, namely that exponentiation, which is a common algorithm, takes cubic time. It's not very fast from a practical perspective. People, in fact, spend a lot of time and effort getting improved algorithms and fast implementations, but it'll do for us. So that's all I want to say about the actual algorithms and the math behind them. And what I'll show you here is the table so that you have it and remember that this is what you need to look up. We don't have to go through it again, but it's there for further reference. Next, we're going to look at a few things that hopefully just give us some practice and tools with both number theory and algorithmic number theory, and with solving problems that often involve breaking things. So the first one is to consider a problem we've often looked at in school, which is equation solving. So suppose I have an equation one variable, like a times x equals c, where x is the unknown and a and c are known. Well, you would usually solve that as saying, well, x is c divided by a. I want to ask the analogous question in the group or some group mod n that we might work with. So here a and c are integers mod n, and I want to solve the equation mod n. So given a and c, determine x so that a times x mod n is c. How would you approach that? Well, could you start by saying something like this? X is c over a. Doesn't quite make sense. Notice that the problem statement said, find the unknown x as an element in Zn. In particular, it has to be an integer. And so this doesn't have to be an integer at all, and that wouldn't work. As an example, suppose n, a, and c were 5, 2, 3 respectively. If you tried to do this, you would get c divided by a, which is 3/2 or 1.5. And that does not make sense in this context because your x has to be an integer. However, if you then just kind of play with it, you might notice that in this example, you can, by guesswork or trial and error, see that there is a solution. For example, x equals 4 works. Why is that? Well, what is a times x? Well, a is 2 and x is 4. So you'll get 8. And what is n? 5. So you have to do 8 mod 5, which is 3. And 3 is also the value of c. So you've checked that it worked. But you might ask, well, is there actually a way to do this rather than just guesswork? And there is, and this is a nice exercise in a little bit of number theory we've learned. So the intuition is that when we wrote something like c over a, we can reinterpret that as c times the inverse of a. And once we reinterpret the inverse as also being in the group, that method becomes correct. So let's go through the details of that. What we do is now make an additional assumption. When I give you this equation, I also tell you that this A over here, which is the public part, is not just in Zn, but in Zn star. Remember, that means that this is a multiplicative group and it has a multiplicative inverse mod n. And we even had an algorithm to compute it, the modular inverse algorithm. I could run that on A and n and get a result, which by definition is A inverse mod n. And now we proceed just like we might with normal numbers. What happens if I take that inverse b and multiply both sides of our equation by b? Well, b times a by definition is 1. So here I just get x. And so I have the equation that x is b times c mod n. And that's it. We've just discovered the value of x. So we solved the equation with a little simple formula. And that's our answer. X is just b times c mod n. We can test our little example. When n, a, and c were 5, 2, and 3, how would we use this method? Well, the a value here is 2. So according to our method, we need to compute the inverse of 2 modulo n, which is 5. So how do we do that? Well, these numbers are small enough that we just guess or look and see. We see that 2 times 3 is 6, and 6 mod 5 is 1. So the inverse of 2 is actually 3. Right? So that's easy enough to compute. Finally, we do b times c. C is 3. So we get x is b times c mod 5, 3 times 3 mod 5, or 9 mod 5, which is 4. And that's what we also had before. But this you can now use for much larger and other examples. If you're curious about these linear equations, one might note that you can't always solve them. What we saw did require a condition that A is in Zn star, not just in Zn, meaning A must have no common divisor with n to apply the prior method. Was that restriction necessary? This says it kind of was, because if A is not in Zn star, there are cases where we can't solve it. For example, if n is 6, and then we're asked to solve 2 times x mod 6 is 3, I claim that there is no solution x in the range Z6. And you can check that out and see. And of course, it doesn't contradict what we saw before, because here the A value of 2 is not in Z6 star.